So first of all, let me ask you this. If I integrate something and then I take the derivative of that, what do I get? What I started with, right? And that's basically what's going on in the second fundamental theorem of calculus. The first fundamental theorem allows us to evaluate the definite integral without having to use the limit approximation that we've been using, where the interval is constant. So like from 0 to 2, that interval would be constant. But the second fundamental theorem allows us to evaluate definite integrals where the intervals are not constant. So in other words, we have the integral from a to some variable of a function with respect to t dt. So what's happening here is something like this. If I draw just a sketch of a random curve, and this I call A right here, then this is fixed. This is just some number, any number, okay? This is fixed. But this one can change. What I'm doing is I'm allowing that ending interval to continue outward this way for as far as I want. So what that means I need to do is take the integral of this function with respect to t, and then I'm going to substitute in x. And the result is I'll get a new function with x instead of t. And then I'll be able to plug in whatever that number is that I want, or a series of numbers in that I want, and I'll find the area here, or the area here, or the area here, or the, and so on, okay? So I'm just allowing the right endpoint of this thing to expand. And then I'm able to evaluate it anywhere that I want, okay? So I'm just using a variable as the upper bound, even though I said earlier that the lower and upper limits have to be constant. So the result is the original variable t, in this case, is replaced by the new variable x, in this case, from the interval that you were given. That's the big key for the second fundamental. So for example, we want to evaluate this function at x equals all of these upper limits. F of x equals the integral from 0 to x of cosine t dt. Notice that I have a t here and I'm integrating with respect to t. But then I'm going to substitute in 0 to x. So the result will be I'll have integrated it, but I'll have the variable x instead, and then I'm going to evaluate it at each one of these as we go along. So it's probably going to be helpful to picture what the graph of cosine t looks like. What's it look like? Starts at 1, okay. So we're up here. Okay, so it kind of does this for one full cycle, right? One full cycle would be how far? 2 pi. So that makes this pi. So the biggest number that we have here is pi over 2. So where is that? Right where we're crossing. So that's pi over 2 there. So what I'm doing here is I'm finding the area under the curve from 0 to each one of these numbers here. So from 0 to 0, the area under the curve will be 0. And then from 0 to pi over 6, the area will be smaller. But then as I grow that upper limit, the area will also grow until eventually I have this whole area right here. What I'm doing basically is just accumulating area under the curve. Okay? All right. So let's go ahead and integrate this. What do we get? Negative sine t? Okay, think about it. The derivative of sine is cosine. So it's positive sine. Right. So yeah, you want to remember that you're going the other way instead. So if I'm looking at cosine, what gave me cosine? Well, sine gave me cosine, but the derivative of sine is positive cosine. So therefore, this must be sine t. And we're evaluating that from 0 to x. So that's going to give us sine x minus sine 0. But sine 0 is 0. So I wind up with sine x. So the area under the curve actually is going to just be the sine of whatever I put in for x.
So then you can plug in all these different.
So then you can plug in each one of those individual numbers.
Not bad.
Yeah. So now that I've evaluated the integral, I can substitute in each one of these numbers, and then I'll get my actual area. There's nothing further to do. So let's go, I don't know, how do you want to do it? We can probably organize this kind of nicely. Make a table maybe. Let's use function notation, whatever you want to do. F at 0 is going to be sine 0, which is 0. F at pi over 6, so sine pi over 6. And what's sine pi over 6? 1/2. Can't do pi over 12 in your head from pi over 6. Doesn't work like that. Because it's a surlcy, not a line. No, I'm out of crying towels for now. So no tears. Next one, f of pi over 4 is sine pi over 4, which is root 2 over 2. Now f of pi over 3, which is sine pi over 3, which is root 3 over 2. And are these numbers getting bigger each time? Yeah. And finally, f of pi over 2, which is sine pi over 2, which is 1. So therefore, at the end, the area under this curve right here is 1. Why do you have to do all of them? Because it asked you to. You can think of what we're doing as accumulating area. Like when I take the sine of 0, I have no area accumulated. But then the sine of pi over 6, I have this much area right here accumulated. And then from 0 to pi over 4, now I have this much area. It's like I'm kind of filling up this area thing as I go along here. Okay? But the point was, once I do this, I can plug in any number of numbers that I want to find the area from 0 to whatever I want. Incidentally, if I were to graph sine, where is sine at pi over 2? Yeah, it's at 1. So remember that the total area here, from here to here, gives me the resulting value of the function that I integrated. Okay? All right, so it's an example of an accumulation function. I've been using the word accumulation. Basically, just think of it as like snowfall or something. As the snow falls longer and longer and longer, we get more and more and more snow built up. That's an accumulation. So think of it like that. Maybe that'll help. But integration is an accumulation over the interval. As I move across, I'm getting more and more area. So officially, the second fundamental theorem of calculus says this. Well, what does that say? The derivative of the integral. So it's kind of like is the friend of my enemy, or is the friend of my enemy my friend? Or is the enemy of my enemy my enemy? It's kind of like that. Really what's happening here is nothing. I'm integrating the function with respect to time, but then I'm substituting in this x. Notice that it's still just some random number right here. It doesn't matter what that bottom number is. It's the top number here that matters. The reason is we're subtracting off that bottom one and then it just disappears anyway. Now I'm going to take the derivative with respect to x. So I've integrated with respect to t, but I substituted in x, and now I take the derivative with respect to x, and I wind up exactly where I started, except my variable now is x instead of t. It's kind of like saying 1 equals 1, kind of. And it doesn't have to be x and t. It can be anything. Really what they're showing you here is I have some variable here. I have another variable here. I can do this process and wind up with that new upper limit as my variable in the original function. Okay, so the simple example. I'm taking the derivative with respect to x of the integral from 0 to x of the square root of t squared plus 1 with respect to t. So what do I do? Do I need to bother integrating all of this mess right here? No, I don't. Can't I just? They're very good. How about we just use what we just learned and say that if I integrate this, and then I'm going to plug in my x, and then I'm going to take the derivative, am I not going to wind up exactly where I started?
Yeah, you are.
And am I going to just see the x sitting there?
Yeah.
This is the square root of x squared plus 1. That's the answer. Okay, so we have another example. Find the derivative of capital F of x equals the integral from pi over 2 to x to the third of cosine t dt. So we see that we have this x to the third sitting here, okay? Now, what we just did with this right here is going to be nice is, remember the directions say find the derivative. So I need to find the derivative of this function right here. Now I got a couple ways I can go. I could integrate cosine t, which would give me sine t, but then when I plug in these numbers, I wind up with that x to the third. So now it's sine x to the third, and then I got to take the derivative of that. Which to do, I need the chain rule. Okay? So this theorem that we're looking at here is a useful way to do something like this that involves the chain rule. Okay. So to do that, what you need to do is realize that what we're looking for is capital F prime of x, right? Okay, capital F prime of x is going to be the derivative of the original function with respect to u. Chain rule. Du over dx. Do you agree? This is the chain rule that we're looking at. If I didn't chain rule this, I just have df over dx, which is exactly what this says right here. Okay? So instead of writing just du over dx, I'm writing this down to like a chain rule problem. Because I have this function sitting right here, which I'm now calling u. Okay? All right. So I can rewrite this. This can be rewritten as d over du of capital F of x. Which we know is this. And then I still have this du over dx here. So right now, what I have sitting here is this guy. Okay? All right. So I'm going to plug this guy in right here. So this gives me the derivative with respect to u of the integral from pi over 2 to x to the third of cosine t dt. And all of that is still having a du over dx hanging on the outside. Okay, so we have this d over du. I need a u. This is my u right here. So now what I have is d over du of the integral still from pi over 2. And remember, this pi over 2 is totally irrelevant here with the second fundamental theorem of calculus. It doesn't matter what this number is at all. It's this one right here that matters. And now that's u. Cosine t dt, and then du over dx. Now that I've called this u, I know what this is right here. I do. Because what is u? So over here I can write let u equal, what did I let u equal? X cubed. So that means that du over dx equals what? 3x squared. So now I know what this is sitting right here. Okay. Now all I got to do is worry about this. Exactly. Because of the fact that I'm integrating from something to u, cosine t dt, and then taking the derivative back, I wind up with cosine u du over dx. And now I know all of that stuff. So I get cosine u is x to the third, but then I have to multiply on du over dx, which is 3x squared. So my final answer could be rewritten then as 3x squared cosine x to the third.
And that is
That's the answer.
the integral
That is the derivative of this function right here.
Okay.
The reason we called it capital F of x is because we're saying we're integrating a function. Okay? So you can go through this whole process to reason out what the answer must be. That's the point, okay? And that is really what the second fundamental theorem of calculus is getting at, is that you can go from something that looks like this to the answer by following through the chain rule. Do we see a shortcut maybe that we can do?
Yeah.
What is it? Yeah, the derivative of this times this with this replaced by this. Okay, so this guy went in there, and then the derivative of this guy went there. It's basically just the chain rule happening. Okay? Here's another wonderful theorem, the net change theorem. We're going to see the net change theorem mostly in story problems, mostly in free response. Usually like particle motion problems or some sort of problem that involves filling up a tank of water or fluid or something, the displacement of a particle, total accumulation of something, snowfall or something like that. Anything that accumulates stuff over time or distance traveled. Okay, so particularly useful in story problems, particle motion problems, basically to find the net change, such as blah, 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 integrate the rate of change that you're given. You'll be given a rate of change as a function. Integrate that from A to B. So from the beginning of time to the end of time that they have in question in the problem. Once you do, just evaluate that definite integral and you'll have your net change. It's actually kind of a straightforward problem. The one last thing I'm going to add about this is because you're dealing with a story problem, there's going to be units involved, so you want to make sure that you have the proper units at the end when you're done. So, and you can usually figure those out just by reading the problem. We have a chemical flows into a storage tank at a rate of, and then we give a function here, in liters per minute, where t is the time in minutes and 0 is less than t is less than 60. Find the amount of chemical that flows into the tank during the first 20 minutes. So what they're doing with this interval right here is they're saying that this function is valid between 0 and 60 minutes. And we want to find the amount of chemical that flows into the tank just during the first 20 minutes. We could extend the problem and say 20 to 30 minutes and so on, but we only care about the first 20 minutes for whatever reason in this particular problem. Okay? And it's going to be the amount of chemical that flows into the tank. So what will my units in the end be? Liters. Yeah. We have liters per minute here. That's the rate. So therefore, it's liters of chemicals that are flowing into the tank. Okay, now they give us this function sitting right here. So what I need to do is integrate that function from 0 to 20. And my function is 180 plus 3t. And I'm integrating with respect to time. So that's the integral right there. Do that problem and you have your answer. So we integrate. We have 180t plus 3t squared over 2 from 0 to 20. Think about the 0. It's going to be gone. So all I got to worry about is the 20. So I have 180 times 20 plus 3 halves, 20 squared. 180 times 20, 3,600, plus 400, 3 halves times 400. 600 sounds good. So 400 divided by 2 first is 200, and then 200 times 3 is 600, for a total of 4,200 liters of chemical. Another incredibly important problem. It turns out this section is actually really, really important. Very, very important. For particle motion problems, and you're going to see a lot of these, maybe not in the homework, but AP exam definitely, there's always at least one, and it's almost always a free response problem. For particle motion problems, it's important to distinguish between displacement and distance traveled. We have to understand the difference in meaning between these two things. What does displacement mean? Yes. It's strictly where did it go compared to where it started. It could have done all kinds of things in between. Like what I could do is I could find a brick or maybe an eraser or something, and I could give it to one of you and then have somebody leave the room. And then everybody else in the room could move that brick from place to place to place to place to place. And then finally, after it's done moving, set it down and go sit back down and have the person out in the hall come back in and look at where that brick wound up. And I could ask them what was its displacement. And they could measure from where it started to where it finished, and that would be its displacement. Would they have any knowledge of how far that thing actually went? No, because they were out of the room. But they know where it wound up compared to where it started. That's displacement. Distance traveled would be like if I had an odometer on that thing and it measured how far it went from place to place to place to place to place. That's distance traveled. Okay? How far did you go? If I went from here to Cody to Basin back to here, how far did I go? A bunch of miles. But what was my displacement? 0. Okay? Even though I move, my displacement can be 0. So this is because the usual particle motion problem will have the particle changing direction at some point. Normally you're going to have some sort of situation where the particle is like, here's my line, and the particle is sort of moving along this line. Maybe it goes to the right for a while, it turns around, comes back to the left, comes back to the right. Okay, that is your typical particle displacement problem. So we need to look at this graph because this graph shows a really good example of the difference between displacement and distance traveled. So let's pretend that this graph is a particle's velocity over the interval from 0 to 2.5. 0 to 2.5. I want to label each area and then we'll talk about what's happening in each region. So, probably would be helpful, I have that line over there, but let's put this particle on this line right here. And we need to talk about the fact that this is the particle's velocity with respect to time. So without getting into numbers, what are we seeing in this graph? Yeah, we're seeing its velocity over time. Maybe more generally. There we go. We have some negative velocities and we have some positive velocities. So we need to realize what that means. Direction. Negative velocity implies a direction. Positive velocity implies a direction as I move along this line. Okay? So in general, we have a coordinate system that we use. This would be positive x and this is positive y. So the direction to the right is positive. Direction up is positive. So if I'm moving to the right, logically, that will be a positive velocity. If I have a negative velocity, then I must be moving to the left. Okay? So to tell the story of this particle between 0 and 2.5 seconds, the particle starts off moving to the right. And it's moving to the right all this way. But its velocity as it moves to the right is decreasing. It's slowing down. And then right here, its velocity is 0, which means that the particle is not moving because it has begun to turn around and start going to the left. And then it starts speeding up to the left until finally here it starts to slow down again. It's no longer speeding up. Does this mean that the velocity of the particle is 0 here? No. But it starts slowing down and the velocity of the particle becomes 0 again here, at which time the particle begins to turn around and go to the right for the rest of the time apparently. Okay? So that is the story of that particle. That's what the graph here is telling us. Now I want to divide this into regions. So let's call this region 1, this is region 2, and then we have this line coming up to here. This little spot right here will be region 3. Now in region 1, if I were to integrate this area, it would wind up being positive. If I integrated region 2, it would wind up being, and if I integrated region 3, it would be, okay. So if I want to talk about displacement from start to finish, where did I wind up? What could I do? Add all the areas together. Just integrate from here to here. True? Displacement gives me the total distance traveled, right? So if my particle started right here, I don't know if it did or not, but if it did, it's moving to the right, and then it turns around and starts moving to the left, but probably not as far as it moved to the right? Because this area looks a lot bigger than this area. And then it turned around and started moving to the left again. That's the path of the particle. So at the end of 2.5 seconds, where does it wind up? Maybe somewhere in here. So if I take this area right here, that will get me to here. If I then add on this negative area right here, that will back me up to here. And then if I add on this little positive area right here, it will push me back forward to here. That will give me the displacement. Okay? So basically we're just going to integrate from start to finish. And that will give me the displacement. That's what this part right here is saying. The displacement on A to B, that interval, is the integral from A to B of the velocity with respect to time.
I thought you said that displacement wasn't, and then you just said
Displacement is how far I went from start to finish, period. So like, where did I go? I was here. At the end I was here. How far is that distance? All the stuff that happens in between, I don't care about. All I care about is start and end. Okay? Now the integral from here to here will give me where I finished compared to where I started. That's what I want. So the result is I'll have this positive area minus this area, because it's a negative area, and then plus this area. That is displacement. So let's talk about distance traveled now. Distance traveled is like an odometer. How far did I actually walk, or how far did I actually drive, or whatever? How far did this particle actually move? In order to do that, I don't want to subtract this area off right here. I want to add that area on. If you're in your car and you drive from here to Basin, and then you turn around and you drive all the way back to the church, and then you turn around again and drive from there past Basin and continue going, does your odometer care that you just repeated all of that distance in between Basin and the church? No, it doesn't. It will still be adding on those miles. And that's what we want to do here. We want to add everything together. So even though this is a negative area, we don't want to call it a negative area. We want it to be a positive area. And the way to do that is to take the absolute value of the function. Because if I have a positive area and I take the absolute value, I get a positive result. If I take the absolute value of a negative area, I wind up with a positive result. And if I take the absolute value here, I still have a positive result. So now I can add all three of those things together. So that's what this is saying here. Add all of those areas together so that not one is being subtracted off. The notation would be the integral from a to b of the absolute value of the function. In order to do that, though, we can't just turn everything positive. That's not how it works. The graph would look like this. If I take the absolute value of a function, this part would bounce up here, and so on. All of the negative portions would bounce to become positive. And now I have a positive area here, a positive area here, a positive area here. Add them all together and I get my total displacement. Okay? The big thing here, or total not displacement, total distance traveled. The big thing here is that I'm taking the absolute value of the function. So, critical, you need to know the difference between displacement and distance traveled, and you need to know how to attack them. All right, example. The velocity in feet per second of a particle moving along the line is given by this function, where t is in seconds. Part A, what is the displacement of the particle on the time interval 1 to 5? Then part B, what is the total distance traveled by the particle on the time interval 1 to 5? Okay, so basically illustrating exactly what we just talked about. The displacement of the particle is going to be straight up integrate from 1 to 5. Because the positive parts and the negative parts will take care of all that distance that we traveled and get us to exactly where we're at. The total distance traveled means I need to find the absolute value of this function right here. A little bit trickier. So let's see if we can get through part A at least. Notice on the graph I have 1 sitting right here. I have 5 sitting right here. So I'm just talking about this portion of the graph right here from 1 to 5. The particle is moving which way as we start off? To the right. So here's my line, here's my particle. We're moving to the right quite a ways. And then eventually we slow down and stop, turn around and start going back. Do I go back as far? No, I just go back a little bit because of that little negative area right there. So maybe I'm like right there. Now I'm showing that above the line, but really that particle is just moving back and forth on that line. Okay? I'm just showing you this so that you can see kind of where we wound up. So my displacement should be more or less than my distance traveled in this case. My displacement should be less than the distance traveled, okay? To calculate displacement, all I need to do is integrate from here to here, because that integral will take care of this subtraction that's going to happen right here. Follow that? Okay. So for part A, just integrate. We're going to have the integral from 1 to 5 of the function, which is t to the third minus 10. By the way, let me back that up. I'm actually not going to go straight into that. I'm going to write this down a little bit more formally. So from 1 to 5 of v of t dt. Okay? That represents that I understand what I'm doing to whoever's grading this in May. Now I can go integral from 1 to 5 of, since I'm given a function, t to the third minus 10t squared plus 29t minus 20. All of that has dt on it. So now I can integrate. This is good practice. Add 1 to the exponent. Over 4. Minus t to the third, so it'll be 10 over 3. Plus okay, minus 20t from 1 to 5. So plug all those numbers in. What is 5 to the fourth? 625. Over 4. $125 times 10, $12.50. Hopefully this is the sort of problem that you can use your calculator on. So I would actually be using my calculator right now. 29 times 25 divided by 2. Not an even number. $725 over 2, and then minus 100. All of that minus all of this. 1/4 minus 10/3 plus 29 halves minus 20. Since you have a calculator in your hand, just set this up and press enter. What do you get? So the answer is 32/3. And we have feet per second as our units here, so therefore it's 32/3 feet. That's the total displacement. That's how far I went from here to right there. Okay, that distance right there. It's not my total distance traveled. That's part B. So to do part B, we're going to have to figure out where we switch to a negative velocity. We need that point right there. How do we do that? Where velocity equals 0. That's right. So we're going to take this guy right here and set it equal to 0 to find exactly where the velocity equals 0. And do not look at that graph and say, well, it looks like it crosses at 4, so how about I just call it 4? No, you can't do that. You have to mathematically show where that thing crosses the x-axis. Because we can't just say, okay, the absolute value here, and that's going to make every number positive. That's not how absolute value works. We are going to take the absolute value of this function, but that means that we need to find out what this area is right here and turn it positive. Because we're going to wind up with a negative area right here. This needs to become positive. Okay? This needs to bounce up here. So then we can add these two things together. We can't do that unless we know exactly where this integral crosses. Because now what's going to happen is we're going to integrate this area, and we're going to integrate that area, and we're going to have the integral of area 1 minus the integral of area 2. Because this is a negative area, and I want to turn it positive. So we're going to go from 1 to whatever this number is right here, and then from C to 5. Okay? That's the idea of where we're about to go. We don't have time to finish that up, so we'll take care of that next time.